let us continue our example using second derivative test. Remember that we formed the discriminant, which is the second derivative of f with respect to x times the second derivative of f with respect to y minus the second derivative of f with respect to xy raised to the second power. So we need to find three pieces of information, then make a decision based on our test. So this is our function, x squared plus y squared times exponential function e to power negative x. Let's take the partial derivative of f with respect to x, which becomes negative x squared plus y squared to power negative x plus 2x e to power negative x. Remember that here you are multiplying two functions together. So you have to apply the product rule. The derivative of e to power negative x is minus e to power negative x. That's how you end up with a negative e to power negative x in the first term. Well, if you factor out e to power negative x, it becomes 2x minus x squared minus y squared. You need to set it equal to 0 along with the partial derivative of f with respect to y, which is your second equation. This is just 2y e to power negative x. You don't have to apply the product rule here and set it equal to 0. But the second equation equal to 0 has only one solution. Why is that? Because e to power minus x is never 0. So e to power negative x is never 0. You just need to set y equal to 0. Perfect. Now substitute y equal to 0 in the first partial derivative that you took here to be able to solve it. So if you set y equal to 0, you get 2x minus x squared times e to power negative x equal to 0. But again, e to power negative x is never 0. So you just need to set 2x minus x squared equal to 0. So x is 0 or 2. So the critical points are 0 and 0, where x is 0, y is 0, your x is 2, y is 0. So you end up with 2 critical points. The second partial derivative of f with respect to x is the derivative of 2x minus x squared minus y squared e to power negative x. But again, you have to apply the product rule, everybody. This becomes 2 minus 4x plus x squared plus y squared e to power minus x. So let me erase this part of the board. I can explain this for you. So when you're taking the partial derivative of these two, you have to apply the product. This is the derivative of 2x minus x squared, which is 2 minus 2x minus 0 times e to power minus x plus the derivative of e to power negative x, which is minus e to power minus x times 2x minus x squared minus y squared. But here you can easily factor out e to power minus x and simplify this as much as you can. That's how you end up with 2 minus 4x plus x squared plus y squared e to power negative x. The second partial derivative of f with respect to y is the partial derivative of 2y e to power negative x, which is basically 2 e to power negative x. So let me erase this part of the board. The second partial derivative of f with respect to x, y You can use either the first partial derivative or the second partial derivative here. It doesn't matter. It is the partial derivative with respect to x of 2y e to power negative x, which is negative 2y e to power minus x. Now, look at the behavior of the graph. So remember that you have two critical points, 0 and 0, 2 and 0. We need to check for each one of them. This table helps us to track what we did, what are the calculations that we have. The critical points 0 and 0. The second partial derivative of f with respect to x at 0 and 0 is equal to 2. Why is that? This is your second partial derivative with respect to x, this quantity here. And this is the second partial derivative of f with respect to y, this quantity here. And f of xy is negative 2y e to power minus x. So basically, you're just plugging different values and doing the algebra. Take a look. If I plug in 0 and 0 here, it is 2 minus 0 plus 0 plus 0, 1 divided by e to power 0, or just 2. That's how you end up with 2 here. Then, the second partial derivative of f with respect to y at 0, it is 2 times 1 over e to power 0, which is 2 again. That's how you end up with 2. The second partial derivative of f with respect to xy or yx gives you negative 2 times 0, 1 over e to power 0, which is 0. That's you end up with 0 here. So you have 2 times 2 minus 0 squared, which is 4. So as you can see, the discriminant is positive. The second partial derivative with respect to x is positive. What's the meaning of that? We are looking at this scenario. The discriminant is positive. The second partial derivative is positive. So you have a local minimum at 0 and 0. So we're done with the first critical point. Now the second critical point, 2 and 0. For 2 and 0, you do the same thing. You start doing the algebra here. So again, just need to clear these and then do the substitution. See what you have. The second partial derivative of f at 2 and 0. 2 and 0. So this is 2 minus 8 plus 4 plus 0, 1 over e to power 2. As you can see, this is negative 2 e to power negative 2, which is a negative number. Now, if you plug in this into the second partial derivative of f with respect to y, this is 2 e to power negative 2, another positive number. And then if you plug that in here, 2 and 0, it is negative 2 times 0 e to power negative 2, which is just 0. Okay, perfect. So your discriminant is going to be negative 2 e to power negative 2 times 2 e to power negative 2 minus 0 squared, which is a negative number. So this is your discriminant, everyone. The discriminant is negative, so you end up with a saddle point. You can visually take a look at the graph here and analyze it based on the graph as well. But when it comes to exam, you need to do all the calculations and show the algebra behind it. So again, we took the partial derivative with respect to x, with respect to y, set them equal to 0 to find the critical points. But again, note that when you set 2y e to power negative x, for example, equal to 0, e to negative x is never 0. So there is no point setting this equal to 0. So you set 2y equal to 0 and y becomes 0. That's how you get y equal to 0 here.